Imagine the ground under your feet moving for 4.5 minutes straight. Not 1 second, not 10 seconds. 4.5 minutes of the earth rolling like ocean waves. This is the true story of the 9.2 Alaska earthquake, the most powerful earthquake ever recorded in American history. And it did things that still sound impossible today. A school split in half and slid 30 feet into the ground like it was made of paper. A whole town watched its main dock disappear into the sea in seconds, taking dozens of people with it. In one small fishing village, nearly 1 out of every 3 people who lived there was killed before the night was over. Somewhere far away, in another country, scientists watched their earthquake machines go completely haywire and had no idea what had just happened on the other side of the world. By the time the ground finally stopped shaking, the coast of Alaska did not look the same anymore. Mountains had pushed upward, whole towns had sunk downward. And racing across the water in the dark was a wave taller than a 3-story building, heading straight for a village that had no way of knowing it was coming. How did one earthquake get so powerful that it changed the actual shape of the coastline? How did it kill people in California thousands of miles from where it started? And why are scientists today still watching this same fault line, waiting to see what it does next? Stick around, because this story gets more unbelievable the deeper we go, and if you want to see more true stories like this one, hit like and subscribe. It genuinely helps and takes a lot of research to bring these stories to you the right way. Let's go back to the beginning, to a quiet Friday evening in Alaska that nobody saw coming. It was Good Friday, March 27th, 1964. Anchorage was a young city, growing fast, home to about 100,000 people. It had grown up quickly around a big Air Force base and the promise of new oil discoveries nearby. On this particular evening, nothing about the city looked like it was about to be hit by disaster. It looked like any other holiday night. Families were sitting down for dinner. Kids were happy because they had the day off school for the long weekend. Downtown, the local J.C. Penney department store was still open, with shoppers walking through the aisles as the winter light faded outside. About 200 miles away, in a small town called Valdez, dock workers were doing a job they had done 100 times before. They were unloading cargo from a supply ship called the SS Chenega, tied up at the town's main dock. Nothing felt strange or dangerous about that evening. Nobody standing on that dock, and nobody sitting down to eat dinner in Anchorage had any idea what was happening deep underground. Beneath their feet, one of the most dangerous cracks in the entire planet had been slowly building up pressure for generations. It was like a giant spring being pushed tighter and tighter, waiting for the moment it would finally snap. At 5:36 in the evening, it snapped. About 25 kilometers below the seafloor of Prince William Sound, near the towns of Valdez and Whittier, a massive crack in the earth gave way. And it did not stop after just a small section broke. It kept tearing, ripping open along a stretch of earth nearly 800 kilometers long. That is an almost impossible number to picture. To put it simply, imagine a crack in the ground as long as the entire coastline of California, tearing open all at once, deep underground, in under 5 minutes. The people living through it did not know any of the science in the moment. They did not know words like fault line or plate boundary. All they knew was that the ground would not stop shaking. Alaskans were used to small earthquakes. Little tremors were almost normal there, since the state sits right on what scientists call the Ring of Fire, a giant horseshoe-shaped chain of cracks and volcanoes that wraps around the edge of the Pacific Ocean through places like Japan, New Zealand, and down the whole west coast of the Americas. So when the shaking began that evening, plenty of people figured it would stop in a few seconds, just like always. But it did not stop. It kept going and going and going. Streetlights along the main road in downtown Anchorage swung so hard back and forth that they touched the pavement. Inside the J.C. Penney store, one woman stood completely frozen as the wall right in front of her cracked open like a mouth. As the shaking continued far longer than anyone expected, people who had felt dozens of earthquakes in their lives began to feel something new rise up in their stomachs. A deep, sinking fear. This one was different. This one was not going to stop anytime soon. When the shaking finally did stop, 4.5 minutes later, scientists at the United States Geological Survey made their first guess at how strong it had been. Their early estimate was a magnitude of about 8.4, which was already a shocking number, bigger than almost anything ever measured before. But as scientists studied it more closely in the following months and years, using better tools and better methods, they kept revising that number upward. It went from 8.4 to something even bigger, and eventually settled at 9.2. That made it the most powerful earthquake ever recorded in the history of North America. Even today, over 60 years later, it remains the second most powerful earthquake ever recorded anywhere on planet Earth, behind only a magnitude 9.5 earthquake that hit Valdivia, Chile, back in 1960. To understand what a 9.2 really means in terms of raw power, consider this. This one earthquake released roughly 1,000 times more energy than the earthquake that devastated Haiti in 2010. 1,000 times more energy released in under 5 minutes. In that short amount of time, an area of southern Alaska larger than many entire countries was permanently changed, geologically, forever. On the other side of the planet, in places like Europe and Australia, machines built to measure earthquakes registered the shaking so strongly that their needles swung completely off the edge of the paper they were supposed to draw on. The waves from this single earthquake actually traveled around the entire globe, more than once. Picture a scientist sitting quietly at a research station somewhere far away, watching a machine suddenly go wild, having no idea that halfway around the world, a school building was being torn apart at that very moment. That school was called Government Hill Elementary, and it sat up on a bluff overlooking downtown Anchorage. Underneath that bluff was a special kind of soil that geologists call the Bootlegger Cove Formation. This soil is a very sensitive type of clay, and under the right conditions, meaning enough water combined with strong enough shaking, it can lose almost all of its strength and start acting like a liquid instead of solid ground. This process is called liquefaction, and that is exactly what happened underneath that school. As the shaking grew stronger and stronger, the clay beneath the building simply gave up. It stopped behaving like solid earth and started behaving like liquid. The school building did not just crack a little. It split completely apart into separate broken sections, and those sections slid downward, some dropping more than 30 feet from where they had started. The whole structure twisted and folded into something that looked less like a school and more like wreckage from a plane crash. Because the earthquake struck on a holiday evening instead of during a normal school day, there were no children inside the building when it happened. If the same earthquake had struck just 3 days earlier on a regular Tuesday afternoon with a school full of children inside, the number of deaths in Anchorage alone could have been in the dozens, or even worse. It was pure timing, pure blind luck, that turned this collapsed school into a case study for scientists instead of one of the worst tragedies in American history. That same unstable ground caused terrible damage in another part of Anchorage, too, a neighborhood called Turnagain Heights. It was one of the nicer parts of the city, sitting up on a bluff that looked out over the water of Cook Inlet. When the shaking hit that bluff, the ground there broke apart into a chaotic mess of collapsing chunks of earth. About 75 acres of land where people's homes sat broke apart and slid in stages toward the sea below. In just a few minutes, 75 homes were completely destroyed. Some were crushed flat. Others were left standing but tilted at strange, frightening angles, sitting on ground that no longer looked anything like the flat, normal yard it had been earlier that same morning. The damage to this area was so severe that the scars stayed visible on the land for years afterward. Today, part of that same site has been turned into a park called Earthquake Park, where visitors can walk around and still see the remains of a neighborhood that the ground itself swallowed up in minutes. Downtown, along the city's main shopping street called 4th Avenue, the street itself dropped more than 10 feet along a crack that opened up right underneath the row of stores. Photographs taken right after the earthquake almost look fake when you see them today. On one side of a giant crack in the earth, cars sit parked normally at street level. On the other side of that same crack, entire building fronts sit sunk far below, like someone took a giant knife, cut through the pavement, and quietly lowered half the street down into the ground. That J.C. Penney building, the same one where a woman had watched a wall crack open right in front of her, lost its heavy stone decorations completely. Those large concrete panels came crashing down onto the sidewalk below and killed one person. And yet, given just how much destruction hit the city, only 9 people died within Anchorage itself. Most of the neighborhoods that were hit hardest by landslides and collapsing buildings did not have very many people living in them. And because it happened on a holiday evening, with many downtown offices and stores standing empty, fewer people were caught inside buildings when the worst damage happened. But as terrible as Anchorage's damage was, it was not actually the main story of this disaster. The real horror of that night was happening across the water, in small towns and villages most Americans had never even heard of, and it was only just getting started. When that massive crack in the seafloor, stretching 800 kilometers long, suddenly lurched upward and sideways, it did not just shake the land above it, it also pushed an enormous amount of ocean water out of place, and all of that displaced water had to go somewhere. It turned into a series of tsunamis, not just one single wave, but multiple waves, moving in multiple directions, arriving at different coastlines at completely different times. And here is the terrifying part. Back in 1964, there was no tsunami warning system anywhere along the coast of Alaska. Nobody was going to call ahead and warn people. No siren was going to sound a warning. The wave was simply going to arrive without any notice at all. The very first place that wave arrived was a small village called Chenega, tucked deep inside Prince William Sound. Only about 76 people lived there. Survivors would later describe shaking so violent that some of them could not even stand up. They were down on their hands and knees on the ground, feeling the earth itself shudder and roll beneath them like something alive. When the shaking finally stopped, some villagers noticed something strange happening in the water nearby. The water in the bay was pulling backward, drawing away from the shore, uncovering parts of the sea floor that no one in the village had ever seen exposed before in their entire lives. Today, scientists know exactly what that strange sight means. A shoreline pulling back like that is one of nature's very last warning signs before a tsunami hits. It is like the ocean taking one giant breath inward right before it comes rushing back out. But in 1964, almost nobody understood what that sign meant. It was not something people had been taught to recognize. To the villagers watching it happen, it just looked strange and confusing. A few people might have sensed that danger was coming, but most of them had no real way of knowing what was about to happen next. About 4 minutes after the shaking stopped, a wave that scientific survey teams later estimated to be over 30 feet tall came rushing through the village. 30 feet. That is not just a wave washing gently over a beach. That is a wall of water taller than most three-story buildings, slamming forward with the full force of an entire ocean pushing behind it. Of the 76 people living in Chenega that evening, 23 of them were killed. Nearly 1/3 of the entire village was gone in just a matter of moments. The physical village itself was almost completely wiped off the map. Homes were splintered apart and scattered through the surrounding forest and water, as if the whole community had simply been picked up by a giant hand and thrown. About 200 miles away, in the town of Valdez, the nightmare happened in 2 separate stages, and each one was just as devastating as the other. When the shaking first hit, it triggered an underwater landslide along the unstable ground that the original town had been built on. This landslide, happening underwater, collapsed the harbor and pulled the entire town dock straight down into the sea. Remember those dock workers unloading cargo from the ship called the SS Chena? Remember how it was just a normal routine job they had done 100 times before? The dock they were standing on did not just crack a little, it vanished completely into Prince William Sound, pulling 31 people down along with it. They drowned or were crushed among broken wooden pilings and falling cargo, and it all happened in a matter of seconds. Some of the people lost were workers doing their jobs. Others were children who had walked down to the waterfront that evening just to watch the big ship come in. Then, as if that was not already enough tragedy for one town, a second wave hit. This tsunami was created by both the underwater landslide and the larger movement of the seafloor from the earthquake itself, and it finished off whatever was left of the waterfront. The destruction in Valdez was so complete, and the ground underneath the town was proven to be so dangerously unstable, that town officials made an almost unheard-of decision. They decided to move the entire town, not rebuild it in the same spot, but physically relocate it 4 miles away, to a new location sitting on solid bedrock. This process took years to complete. It basically meant rebuilding an entire American town from scratch in a brand new location, something that had almost no precedent anywhere else in the country's history. The town of Seward suffered its own combination of disasters, one right after another. The shaking there destabilized the waterfront, where large fuel storage tanks belonging to an oil company sat on loose fill material. That material, just like so much of the coastline that terrible night, was extremely prone to liquefaction. The fuel tanks ruptured, fuel spread out across the surface of the harbor water, and then a landslide-generated wave, created locally, combined with that spilled fuel which then caught fire, creating a moving wall of burning water that swept through the harbor. Survivors who watched this happen later described it exactly how it sounds. It looked like the sea itself had caught on fire. Railroad tracks, warehouses, the town's small boat harbor, all of it was consumed by this terrifying combination of water and flame. Further south, the town of Kodiak was hit by a series of tsunami waves that flooded the downtown business area and tore through the town's entire fishing fleet. This was a devastating blow to a community whose whole economy depended on fishing and the sea. Docks, fish canneries, and dozens of boats were destroyed or swept away, all within a matter of hours. For a small fishing town like Kodiak, that kind of damage is not just about broken buildings. It is the loss of an entire way of making a living, an entire season's income wiped out in one single afternoon, with effects that would ripple through the local economy for years to come. And the waves did not stop once they reached the edge of Alaska. Traveling at speeds faster than 400 miles per hour across the open Pacific Ocean, these tsunami waves reached the coast of Oregon in roughly 4 hours, and Northern California shortly after that. In a town called Crescent City, California, people had already lived through a couple of smaller waves earlier that night. Believing that the danger had passed, many of them went back to their homes and shops to check on things. That is exactly when the fourth wave arrived, the biggest one of all, measuring more than 20 feet tall, and it hit without any real warning system in place to keep the streets clear. There was no functioning tsunami alert network anywhere along the entire west coast of the United States at that time. 11 people died in Crescent City that night. To this day, it remains the single most damaging tsunami event in California's entire recorded history, and the waves kept traveling even further than that. Tide gauges over in Hawaii picked up measurable surges of water nearly 6 hours after the earthquake first struck. Places like British Columbia, Washington, and Oregon all recorded the earthquake's effects along their own coastlines. And on the completely opposite side of the entire Pacific Ocean, the country of Japan recorded small but clearly detectable tsunami waves from this same earthquake, arriving many hours later. Think about that for a moment. An earthquake that started underneath the seafloor of Prince William Sound, Alaska, sent waves all the way to the coast of Japan. That is how much energy was let loose in those 4.5 minutes. That is how far a single crack in the Earth's crust can reach once it sets an entire ocean into motion. When the final numbers were counted, the earthquake and the tsunamis it caused had killed approximately 131 people. And here is the detail that would go on to shape decades of American disaster planning afterward. The overwhelming majority of those deaths were not caused by the shaking itself. They were caused by the waves that arrived hours later in places far away from where the earthquake actually started, among people who had absolutely no warning system to tell them what was coming toward them. In the weeks after the disaster, something else started happening. Something quieter, slower, but in its own way, just as important as the earthquake itself had been. The United States Geological Survey sent a young geologist named George Plafker to study the huge area of ground that had been deformed across southern Alaska. Plafker had already spent years working in that region, and almost immediately he realized that the scale of vertical land movement he was documenting was unlike anything ever recorded from a single earthquake before in human history. For months, traveling by boat and by small plane across a rugged coastline with almost no roads, Plafker and his colleagues from the USGS carefully mapped out exactly where the land had risen upward and where it had sunk downward. They did not have satellites or GPS technology to help them do this kind of work back then. Instead, they used something much simpler. They studied barnacle lines on rocks, which show the visible line where sea creatures could survive and where they could not, along with old tide gauge records and shifted shoreline features. They were basically reading the coastline itself like a measuring tool that nature had built all on its own. What Plafker discovered was incredibly consistent and, in its own way, shocking. Some regions, especially on the seaward side of the crack near Montague Island, had been pushed upward by as much as 38 feet. 38 feet of solid ground, lifted up in under 5 minutes. This was the largest tectonic uplift ever documented from a single earthquake at that point in history. Other areas told the completely opposite story. A small community called Portage, southeast of Anchorage, actually sank down by several feet, which permanently changed the level of the local water table. Salt water began seeping into ground that had never experienced salt water before, and it poisoned the roots of an entire forest of spruce trees. Those trees died while still standing upright. Their gray, bare trunks are still standing there today along the Seward Highway, a haunting stretch of land that people who live nearby now simply call the Ghost Forest. Even 6 decades later, you can still drive right past it and see it with your own eyes. This pattern, land rising up on one side of the crack and sinking down on the other side, was not random at all, and Plafker recognized that immediately. It matched, with striking precision, the exact pattern that scientists would expect to see from something called a subduction zone earthquake. This is the kind of earthquake that happens when one giant piece of the Earth's crust, called a tectonic plate, gets forced underneath another one along a huge, gently sloping crack deep below the surface. Here is why this discovery mattered so much to science as a whole. Back in 1964, the theory of plate tectonics, the idea that the Earth's outer crust is broken up into massive moving pieces that drift, crash into each other, and grind against one another, was still being figured out by scientists. It was built on older ideas about continents slowly drifting apart, first suggested by a scientist named Alfred Wegener earlier in the century, and it was starting to gain more support because of new studies looking at the seafloor and strange magnetic patterns found in the rock deep under the ocean. But plenty of geologists at that time still doubted the whole idea. It had not yet become the widely accepted scientific fact that it is today. Plafker published his findings in a scientific paper in 1965 in a journal called Science, based directly on the field work he had done out in Prince William Sound. His explanation suggested that the 1964 earthquake was the sudden release of centuries' worth of built-up pressure along the exact boundary where the Pacific plate was slowly being pushed underneath the North American plate. And the pattern of land rising and sinking that he had spent months carefully mapping out matched almost perfectly with what that new subduction theory predicted it should look like. It is one thing to argue for a scientific idea using abstract models and scattered bits of evidence gathered from all around the world. It is an entirely different thing to actually watch the ground rise 38 feet in one place and sink several feet in another place, in exactly the pattern that a brand new theory said it should. Within just a few years after this, the wider scientific community had largely accepted plate tectonics as the main way to understand earthquakes and volcanic activity happening all across the entire planet. Historians who study the history of science often point to the 1964 Alaska earthquake as one of the key natural events that helped make that widespread acceptance possible, alongside other groundbreaking research happening at the same time by scientists studying magnetism on the seafloor in completely different parts of the world. In short, a single earthquake in a remote American state helped confirm one of the most important scientific ideas of the entire 20th century. But the earthquake's impact was not only about science, it also permanently changed how the United States approaches both earthquake engineering and disaster warning systems. Investigators studied the terrible building failures across Anchorage in great detail, especially the buildings that had been built on that dangerous bootlegger cove clay. And what they learned fed directly into brand new building codes at both the federal and city level for construction on ground that was prone to liquefaction. Engineers who studied the collapse of concrete buildings downtown, many of which had been built under old standards that never accounted for shaking this strong or this long-lasting, produced research that went on to influence earthquake building codes not just in Alaska, but in earthquake-prone areas across the entire country. These are codes that are still shaping how buildings get constructed today, more than 60 years later. And the almost total lack of any working tsunami warning system, which was the single biggest factor blamed for the slow, chaotic evacuations, both in Alaska's remote coastal villages and all the way down in Crescent City, California, led directly to action being taken by Congress. It resulted in the creation of the Alaska Tsunami Warning Center in Palmer, Alaska, which officially became operational by the year 1967. That facility, along with a sister center covering the wider Pacific region, is today part of a much larger tsunami warning network run by NOAA, a system that now covers the entire west coast of the United States and all of Alaska. Much of the infrastructure that now sends out tsunami warnings within just minutes of a major offshore earthquake, things like networks of pressure sensors sitting on the ocean floor and coastal tide gauges that constantly send data back to scientists, simply did not exist back in 1964. That entire modern warning system can trace its origins directly back to the failures that were exposed by this one earthquake. Every single person who has ever received a tsunami warning alert on their phone owes that warning, in some indirect way, to the hard lessons paid for by the people of Chenega, Valdez, and Crescent City. But here is the part of this story that should genuinely make you uneasy. Even 6 decades later, scientists are still asking urgent questions about what the 1964 earthquake means for the future. Modern GPS technology and satellite measurements used by researchers at the University of Alaska Fairbanks and other institutions have shown that parts of the Alaska-Aleutian fault zone are continuing to build up pressure in patterns that closely resemble the conditions that existed right before 1964. The fault did not finish its work that day. It is still loading up, still building pressure, right now as you watch this. Some sections right next to the 1964 rupture zone, especially stretches further west along the Aleutian Islands near the Semidai Islands and the Chemagan Islands, have not produced an earthquake anywhere near this size in the entire history of recorded measurements, and researchers are genuinely divided over what that actually means. Some scientists believe these sections might be capable of something called silent or slow slip movement, which means they could gradually release their built-up pressure over a long period of time without ever causing one single massive earthquake. Other scientists believe these same sections are completely locked in place, quietly building up more and more stress toward a future earthquake that simply has not happened yet. Whether a section of the fault like that is even capable of producing an earthquake on the same scale as 1964, and what kind of timeline that might happen on, remains a genuinely unresolved question that scientists are still actively researching today. Even with today's far more advanced network of GPS stations, earthquake sensors, and instruments sitting on the ocean floor constantly monitoring this region, nobody can give you a guaranteed answer about when or if it will happen again. Scientists have also turned to an entirely different field of study that barely existed in any real organized way back in 1964. It is called paleoseismology, which is the study of the physical clues that ancient earthquakes leave behind, long before any written or scientific records ever began being kept. By digging into coastal marshes and peat bogs along Prince William Sound and the Kenai Peninsula, researchers have found buried layers of sand and ocean sediment that were left behind by ancient tsunamis, sandwiched between regular layers of soil that formed during quiet, calm periods between these events. By using a dating method called radiocarbon dating on these different layers, geologists have managed to piece together a rough timeline of major earthquakes along this same stretch of the Alaska-Aleutian fault, stretching back well over 1,000 years into the past. And what that timeline suggests is unsettling in just how simple it is. Earthquakes on the same scale as 1964, or even bigger, have happened before in this exact region, more than once, separated by long centuries of quiet calm in between. That longer view of history has reinforced one main conclusion among scientists. The Good Friday earthquake was not some rare, random, one-time event. It was just one earthquake in a long, repeating cycle that is written directly into the layers of sediment beneath the coastline. A cycle that will, at some point far in the future, produce another earthquake in this exact same region. Nobody can tell you exactly when that will happen, but the geological record says, without a doubt, that it will happen again someday. Back in 1964, though, long before any of this newer research ever existed, the immediate challenge facing Anchorage was much simpler to describe, and yet much harder to actually solve. How do you rebuild an entire city when the ground itself has just proven that it cannot be trusted to safely hold that city up anymore? In the days following the earthquake, a federal task force made up of engineers from the USGS, along with outside consultants, began surveying just how much ground failure had happened across the city. What they discovered was deeply concerning. Large sections of Turnagain Heights and the area surrounding 4th Avenue downtown sat on top of soil that, under the right combination of water and shaking, could liquefy all over again in some future earthquake. City officials found themselves stuck in an almost impossible position. Residents were desperate to rebuild their homes quickly. Local businesses were anxious to reopen their doors and get back to normal. And in the middle of it all stood engineers, urging everyone to be careful about exactly where and how any new construction should happen. The compromise that eventually came out of all this was, for its time, almost unheard of. Some of the most badly damaged land, including a large part of the Turnagain slide area, was officially declared permanently unsuitable for any new homes to be built there. Other neighborhoods were allowed to be rebuilt, but only after extensive work was done to stabilize the soil underneath them first. This was one of the very first times in American history that an entire city's rebuilding plan was shaped directly by maps of geological hazards, rather than simply following old property lines and what made the most economic sense. And the example this set went on to influence how other earthquake-prone American cities, including several cities in California, approached zoning laws in risky areas for decades afterward. Even the basic paperwork used to describe the geography of the region had to be completely redone. The National Geodetic Survey spent years remeasuring official elevation points all across southern Alaska, because points that had served as fixed, trusted elevation markers for decades were now, overnight, suddenly meters higher or lower than what the official records had always shown. That might sound like a boring, bureaucratic detail, but it really was not. Roads had to be rebuilt, and not just in the spots where the pavement had cracked. In some cases, entire roads had to be rerouted completely, because the land underneath them had permanently changed its elevation relative to sea level, which changed drainage patterns and even changed how far the ordinary tide would reach along the coast. And underneath all of that science and all of that new policy and all of that reconstruction work, there was a human cost that no official death count could ever fully capture. Thousands of Alaskans were left homeless in the weeks that followed the earthquake. They were taken in by relatives or housed in temporary shelters run by the military and local communities, all through a bitterly cold spring season. Fishing families over in Kodiak and all along the Sound, whose boats and fish canneries had been completely destroyed, lost not just their property, but an entire season's worth of income. It was a blow that rippled through these small coastal economies for years and years afterward. Earthquake and tsunami insurance at that time was rare, and often far too expensive for most families to afford. This meant that many families had to rebuild their entire lives, using nothing but their own personal savings, help from their local community, and federal disaster relief programs that were, back in 1964, still fairly new and mostly untested at this kind of massive scale. In many ways, the response to this earthquake became a testing ground, almost like a live experiment in how the federal government responds to a major disaster, one that would go on to shape and expand disaster relief policy for every major American disaster that came after it. If you stand today at Earthquake Park in Anchorage, you will find a quiet, grassy stretch of land dotted with small informational signs overlooking the water of Cook Inlet. Nothing about the peaceful scene screams disaster at first glance. Birds build nests there, families walk their dogs along the paths. But underneath all that grass lie the broken remains of 75 homes that slid into the earth in under 5 minutes on one single Friday evening back in March. If you drive south along the Seward Highway, you will pass right by the ghost forest, those gray, leafless tree trunks standing in complete silence, killed by salt water that arrived the very moment the ground beneath them suddenly dropped. And far out along the Aleutian Islands, hundreds of miles away from either of those places, the very same fault that ruptured back in 1964 is still sitting there today, still slowly loading up with pressure, still being closely watched by scientists who, even 6 decades later, still cannot tell you exactly when it is going to let go again. The 1964 Alaska earthquake did not just destroy towns and take 131 lives in a single evening. It completely rewrote how humans understand the very ground beneath their own feet. It proved, in real time, that entire continents actually move. It proved that oceans can carry the energy of a single earthquake across 10,000 miles of open water. And it proved that a small village of just 76 people could lose nearly a third of its entire population in the 4 minutes it takes one wave to cross a bay. It forced an entire nation to build warning systems it never thought it would ever need, and building codes it never thought it would ever require. And somewhere out along that same quiet, remote stretch of the Alaska coastline, the fault responsible for all of it is still down there right now, still building, still waiting.